So I'm going to go ahead and kick off the first in our series, the Joseph P. Nicoletti Speaker Series, where we're going to be discussing aspects of the construction of the San Francisco-Oakland Bay Bridge. I'm a representative of Caltrans. Caltrans is part of the Toll Bridge Program Oversight Committee that's managing this project. That consists of California Department of Transportation, the Bay Area Toll Authority, and the California Transportation Commission. They would all like to welcome you tonight. Thank you for coming to the first in this series. And the topics that we're going to cover tonight are, first and foremost, a construction update. We're going to run through some of the things that are happening right now on the bridge so that as you commute over it, you've got some perspective on what exactly the work is. So that's a big part of this. Low transfer is one of the focuses, but there's other things going on as well. And then the other topic that we're going to cover in depth tonight is quality. How do we achieve quality on a project of this magnitude? How do we get quality steel? How do we get quality concrete? And how do we deal with issues when they come up? And my team, the communications team, will do brief little snippets on this. What we're doing tonight is something much more in-depth. It's an opportunity to hear from our engineers' perspective how we tackle these types of situations. How do we set out to achieve what we want for this bridge? And one of the things that we want to communicate right off the bat is how special the new Bay Bridge is. There's no other structure like it in the world. It's the pinnacle of seismic technology when it's ready in 2013. It's been constructed while 280,000 vehicles go across it every day. And we are constructing this bridge in some cases in places where that traffic is already going across. So how do you keep the vehicles moving when you have to put a massive bridge structure in the exact same footprint? It's a big challenge for this job. The engineering is perfectly married with this bridge. So without further ado, I want to introduce Dr. Brian Maroney, who's going to be going over several of these elements that I just spoke about tonight. He's held several different titles in the period that he's worked on the Bay Bridge, but he's one of our senior designers. So, Brian, if you're ready, come on up.
I wanted to participate in respecting and celebrating Joe Nicoletti. I knew Joe Nicoletti long before the Bay Bridge got started, at least the way it is we know it now. This is the image that I always like to start a lot of projects or a lot of presentations with. But what it does, it tells me a story about how I got to know Joe Nicoletti. This is an image of the San Francisco-Oakland Bay Bridge that collapsed in 1989. It was unacceptable, tremendous impact to the Bay Area. And from this, a statewide Governor's Board of Inquiry was launched into how things worked. Or how things didn't work around the Bay Area. Both those are lessons. And a report was released. And then a governor's directive offered several recommendations and basically gave direction to Caltrans about doing things differently statewide for seismic safety. And one of those recommendations was to develop a statewide external independent seismic advisory board. It was chaired by George Hausner, professor back then down at Caltech, who some people know as the father of earthquake engineering, appropriate leader for that group. On that panel, Mr. Joseph P. Nicoletti was appointed even though he was a full-time structural engineer in the Bay Area, very active in organizations like the Structural Engineers Association in Northern California, but he still found time to basically give his time to public service. And that's how I got to know him when he was appointed, because back then, after the 1989 earthquake, I was a young senior bridge engineer with black hair. So I was a lot younger and I was carrying my boss's briefcases, Jim Roberts and Jim Gates. But I actually, even though the issues were difficult, it was just an honor being in the room with people like Joe Nicoletti. Now, that was 1989, dealing with all the things that were going on after Loma Prieta. But then in '92, we had Petrolia earthquake. And that board continued to work, so did Joe. So I had continued interaction with him. Then 1994, Northridge hits. Then we had more continued action. Then after that, after Northridge, about the beginning of 1995, I know I was moved down to the San Francisco-Oakland Bay Bridge to work on the east and west sides as a bridge engineer. And when I was moved in, I saw the Toll Bridge Seismic Safety Peer Review Panel, which is a different kind of group. It's an external independent group that looks over the shoulders on project or program specific. It's not statewide like the Seismic Advisory Board. It's a project or program independent external review panel. Joe Nicoletti was made chair of that. So he was the chair of that, and that's how I got to know him. And I think if we're going to have a respect for him, I think it's good for everybody maybe in the series to talk a little bit about how they got to know Joe. If I can have the next slide. Okay, that Toll Bridge Seismic Safety Peer Review Panel is chaired by Joe Nicoletti. That's a picture of him up at the top. These are the other members that he works with on that panel. Jerry Fox on the top left, Ben Gerwick on the right, top right. They have passed away. Of course, I want to respect to them. Now, about Joe Nicoletti today, when Bart and I were talking about opportunities, we did talk about all the bridges. He's participated up and down the state of California on many jobs, sometimes working in groups on bridges. He's also worked on or helped us with Dunbarton, Richmond, San Rafael. We could look at all the bridges in the Bay, but we decided in the short amount of time we have and the information that we have access to and what we're looking at, we thought, you know what, it's appropriate that we talk about what his contributions were on the Bay Bridge. So I'm going to use the Bay Bridge as a backdrop. And what I want to do is I want to give you a whole series of challenges, because that's what engineers do. Joe Nicoletti is an engineer. He's an incredible gentleman, but he's an engineer. And I want to talk about what engineers do and what Joe did. When you have a multi-billion-dollar job, you do a million different things. And let me tell you, just like at home or just like wherever you work, you don't do a million things and everything goes right. So there's always challenges. That's why we have engineers and technicians out, all the way through design, all the way through construction, and then we keep engineers and technicians around to maintain bridges long afterwards. So I'm just going to pick about 6 or so where you see something about the Bay Bridge, and you also see what Joe did or what his contributions were. I also not only want to talk a little bit about Joe, but I want to highlight how we got here on the Bay Bridge, where we are in the progress of the Bay Bridge, how does it work, and what's hot. And what's hot is really load transfer and quality. And Joe's been involved in every single one of those. First of all, every good hero, like Joe Nicoletti, needs, every protagonist needs an antagonist, right? If Joe's the good guy, the bad guys, it's always important to understand when you're working on a seismic safety project who the bad guys are. And the bad guys are these faults. This is a map. This is a map of northern part of California. These are representative faults. This is, for example, the Hayward. These are San Andreas. And Joe, I don't know if everybody knows, but he was on SEOC seismology committee. So he's made a lot of technical, I would say, public service contributions beyond just the toll bridge program. He's done it in professional organizations, particularly for the building structural world. He was a very successful, and he's retired now, but he's still respected in the structural building community, worked on hospitals, et cetera. So he's quite familiar with the seismology and the risk here. And he helped pass a lot of the building technology to me, my world, the bridge world, okay, as well as the information that he has on seismology. Okay, so Bart and I decided we're going to focus on the Eastbound Seismic Safety Project and overlaying with the work that he did. Next slide. Well, the first challenge is when we got into the Bay Bridge, we had a decision to make. Do we retrofit or do we replace? That's a very difficult decision to make. I want to walk through some of the things that Joe led us through. Next slide. How does society select a bridge? Okay, I'm a bridge designer. Okay, I don't get to choose the bridge. Neither does an architect. Federal law, NEPA, National Environmental Policy Act, tells us we need to reach out and work with communities, and that's what we do. So we have to build consensus, just almost like an election. It's almost a perfect class in US government. How do things work? It's very complicated. Now the community, society around the Bay Bridge is not just San Francisco and Oakland. It's all the users, people who pay tolls on all the toll bridges. It's also all the people in California. It's on this job during the environmental process, we actually ended up reaching out to Washington, D.C. Okay, so the community was very significant. Next slide. Okay, what we do is first you have to recognize a need, then you have to plan, scope it out, and have an environmental evaluation. And that's not just birds and fish. It's the whole environment, the community, okay? What has been there, what is there now, and what's going to be there in the future. Social, economical, et cetera. It's the full total environment. Then you develop complete the design, then you move into construction. Next slide. Hey, on this job, normally that's done one right after another. First you do one, then you do the second one, then you do the third, then you do the fourth. That's what's normal, okay? And it takes a long time, okay? In this case, because we were one of the Governor's Board of Inquiry's recommendations that the governor back then endorsed through a governor's executive directive was exceed quickly, right? The report was actually called a race against time. So there was a lot of pressure to hurry up. Okay? So what we did is we did things in parallel. Not only do we reach out to the public, part of the community, we also reached out to, we followed through an environmental process that matches federal law, NEPA. Then we also started the engineering and design first. Remember the bullets I showed you that the design comes a little later. You do some preliminary work, but then you start the full design later. We actually engage that simultaneously. So you have to work a little harder, it's a little more complicated. You have to have 3 balls in the air instead of just 1. Next slide. Okay, we went through all of the environmental types of studies that you have to do: water, noise, air, visual, energy, costs, archaeology, etc. Next slide. With that, for the first time, we actually used probability. We actually used statistics. And this is a simplified version of actually what we used. This one is really more of a decision tree, but we actually have the full version of this where we actually had probabilities of things like an earthquake right in the middle of construction or in the middle of design. Some things you can't control when an earthquake hits, but you can control what kind of bridge you're going to choose. Is it a self-anchored suspension bridge? Is it a skyway? Is it a cable stay bridge? Which alignment you might choose? Are you going to retrofit the old? Or are you going to replace? And one thing that we clearly all understood and evaluated was if you go with retrofitting the old structure, you can retrofit it, but you're never going to get the same as a new bridge. You can get a higher performance with the new bridge if you choose to. And all of the new bridges allowed that higher level that the Governor's Board of Inquiry recommended for important bridges like the Bay Bridge. Next slide. Now that information literally went to community leaders, all the way up to community leaders. And next slide. That came down to the Metropolitan Transportation Commission. And then they created a Bay Bridge Design Task Force, some elected, some appointed community members. And they were a subset of the full MTC, okay, that was going to formalize that recommendation up to the full commission and then back up to elected officials. Next slide. They had a whole host of decisions to consider. Things like, should it be open and a single level structure? Should it be double deck? Should it be steel? Should it be concrete? Should there be long spans? Should there be short spans? Should you have a bicycle pedestrian facility? Should you not? Should you have trains? Should you not? Should you have more lanes than 10 lanes, etc.? Next slide. They turned to an EDAP, an international group of experts, architects, planners, engineers, okay, some of the most famous bridge engineers in the world. Joe Nicoletti was the chairman of this. Okay? So if you can imagine a group of international architects, planners, and bridge engineers all trying to build consensus with community members, community input from interested parties, other stakeholders, and then interacting with selected community leaders that are elected, appointed. Okay? Building consensus with all of that, that's quite a challenge. Next slide. He did it. He did it in about a year. I worked in Southern California on 710 about 15 years ago, 20 years ago. It's still not completely through that process. That process can regularly take decades. Doyle Drive, they tried to replace that. People were thinking about replacing Doyle Drive 4 decades ago. This consensus was built in unbelievable time. That takes leadership. And it's interesting, one of his best gifts as a leader, in my opinion, was his ability to listen. He let everybody make their contribution, and then he would evaluate and consider that. I think that's very interesting. A strong leader, and one of his best gifts was a listener. And that recommendation went up back through the entire process that I summarized here briefly, and it went to the highest elected officials in the state of California with blessings from Washington, D.C., and legislation was passed. Then the vision was created, and it was accepted, and there was consensus around it. It's unbelievable when I work around the Bay Area, or I go any place and somebody finds out, or I hear somebody finds out I'm working on this bridge, how many people say they love this design. I just think the people that were involved in that consensus building is amazing. Incredible challenge, and he had a huge part of that success. Next slide. So now we have the vision. Okay, and it even had a bicycle pedestrian facility. Next slide. Okay, let's talk a little bit because I want to get into some of our challenges, more technical ones, and I would like to, I need to give you a little background, so I'm going to make sure I give you a little extra information here just to give you some background. Okay, this is something that Jay Mirza and I created a long time ago. It's a very simple side view, and we call it an elevation view. This is a view from the top. This is called a plan view, and what Jay and I did is we broke it up into 4 general categories, and the reason we did this was because a lot of people think, oh, I want one bridge across the whole bay. I want one bridge across the site. And sometimes that happens, but it doesn't usually happen. Some people talk about, for example, the Golden Gate Bridge. Oh, it's one bridge. Well, no, it's not. If you really look at it, it's a collage, right? There's an arch bridge in one area. It's a suspension bridge in another area. It's a viaduct in one area. It's a deck truss in another area, right? And that's because there's a different problem in each one of those areas. Okay? So it makes sense there's a different solution at each one of those locations, right? So it's very common for bridges to have different types of parts or frames, we call them, along the length of a bridge. So we start here. Let me start here at Yerba Buena Island. We call it Yerba Buena Island Transition Structure because fundamentally the operator transitions from double deck in the tunnel, and then the lower deck has to move out, and then once it's clear, then it can start to come up. And that takes safe distance, safe traveling time. So there's a very complicated transition on Yerba Buena Island. That, to me, is sometimes the most interesting part of the structure to me because of those unusual challenges there. And the geology is very, very changing over there. Then there's what we call the main span or the main frame. The forward span is very long. It's about 1,000 feet, and that's because it's a primary deep water shipping channel. Okay? Or at least it's deep right at that location. Right? So it's a primary shipping channel, so that's the justification for 1,000 feet, a 1,000-foot long span, and a taller structure. Okay? And then the back span, it's a much shorter one, about 180 meters. Okay? And it doesn't have to be very long, and it also ends up essentially balancing out this long span. Then this part of the structure, what we call the Skyway, which is most of the structure, it's a little over 1¼ miles, and it's side-by-side structure. It's over variable water depths that range from a couple of meters deep here to on the order of about, it's almost 40, 50 feet, depending on how much scour there is at the end of the bridge. So it has a very different kind of geology than this structure does. These are on rock. All of these are on mud. So the structure is different. It's a different problem. And you don't have deep water ports. They're not primary shipping channels. So again, it's a different problem, okay? And we also don't need to have very long spans, okay? These are on the order of about 500 feet, and they get a little smaller over here. Now over here on Oakland Touchdown, this is a much simpler bridge, shorter spans, okay? The foundations are on land. Most of them are on land, and they go into various types of sands and clays. It's a man-made mole structure, which is a structure that man makes that goes out into the water, okay? Now over here, the structure of the spans are very short. Well, why would you want little short spans over here when you have these beautiful long ones over here? Why? Well, you want longer spans, 500-footers here, not because of the shipping channel, but because in these kinds of soils, a foundation is really expensive. It's really expensive. So you don't want to have a lot of foundations. You don't want to touch the ground a lot because it's cheaper to have a longer span. If you can remove a few piers, you're going to save some money. Okay? Now, when you have a longer span, the superstructure has to get deeper. Okay? So this is still a pretty deep structure. Now, when we get over here, okay, here we've got a different problem. Now we're transitioning, we're touching down on the shores of Oakland. Okay? Well, the top, think about car traffic. The car traffic has to run across the top of the bridge. The cars don't understand or feel or use how deep the structure is as an operator. But over here, the top of that structure better be on land, right? Eventually, you have to get off the bridge, right? So the top of that structure has to get to the roadway. It has to get down to land. You don't want it up in the air anymore, okay? So you don't need a very deep structure. You don't even want a very deep structure because if the structure depth becomes too great, then you actually have to dig out holes in the ground, work with, typically hazardous material or all kinds of strange things when you dig up soils. So you don't want to start digging holes just to allow for greater superstructure. So you have a thinner superstructure, so you don't have to do that. That leads to shorter spans. So that's why in this part of the structure, we anticipated shorter spans and shallower structures so the traffic can move onto the ground smoothly and we don't have to dig into the ground to do that. Next slide. That's a little background. Okay, now the vision that Joe Nicoletti and the other type selection folks had, this is what they developed. Okay, and the self-anchored suspension bridge is pretty fantastic. It's the architectural hub, the architectural center. The vice chair of the EDAP group was John Cricken, who's an architectural planner. He's a senior partner at Skidmore, Owens & Merrill, and he was on that group because of, he's a member of the design review board at PCDC. Next slide. Okay, I've already told you the forward span is very long, 385 meters. The back span's about 180 meters. Okay, part of it's on rock, short. Main tower here. The green is rock. Here you see the muds, the water, and the various lenses of sands and clays that make up the rest of the bay. The rock continues to drop off elsewhere. Pretty exciting structure with the cables. And I think we have a couple of nice architectural boards out in the lobby. Okay, next slide. Okay, the Skyway structure itself, very sleek. Variable depth, chiseled towers. Pentagon, the pentagon shape is almost the architectural vocabulary of this bridge. Even though there's reason for the structural bridge portion of the bridge to be different, the foundation to be different at different locations along the length of the bridge for technical reasons, well, that's the challenge now the architect has to bring the experience of the user to a sense of it's one bridge. Okay? And architecture is one way to do that. And that's really important. So there are elements that you'll see along the length of the bridge, like for example, fantastic light standards, light poles, if you will, elements of the bicycle pedestrian facility, the columns along the Skyway as well as the Oakland Touchdown and YBI. I would say they reflect and they participate in the architectural vocabulary that the tower is the center of. Why are these variable? Why are these variable depths? And this was quite a debate in the EDAP group. A lot of people did not want variable depth. They wanted one straight line. But to get to these long spans, you need to have this variable depth for it to be efficient at all. And the reason for this is a simple one might be if you just hold out your hand and you think about your arm and how it works. Okay. Is this part of your arm a little bigger than your wrist? Yes. Okay. Nature shows it. A tree branch, it's the same way. The tree branch is largest at its support levels. Okay? That's why this is deep. There are reasons through stresses and strains and engineering reasons that this needs to be deep to handle the stresses and strains. Next slide. The transition on the island, which is actually to me one of the most interesting parts of the bridge. Okay, here's the transition area. Okay, and the westbound structure coming this way, this is where these two have to separate away from each other horizontally to get the truck clearance. Once you have the truck clearance vertically from the top of this deck to the bottom of this soffit, then you can start to move up where they meet approximately at the same level at the west end of the self-anchored suspension bridge. Then you see an on-ramp. Okay, next slide. Okay, if you were to cut that section and look at it, this is what you would see. This is the upper deck. This is the lower deck. This is eastbound. This is westbound. This is the on-ramp. Pretty unusual situation. So the Yerba Buena Island, even though people forget about it, it's a very challenging piece of work that Joe's been part of through type selection, design, as well as construction. Next slide. Oakland Touchdown, cross-section, very similar. Details to the Skyway and YBI. Next slide. Okay, now let's get into some of the earthquake engineering. Again, Joe was chair of the Toll Bridge Seismic Safety Peer Review Panel, and this is my philosophy of earthquake engineering. Seismic sources, I need to know about where the faults are. I need to know about what the scenarios are, what kind of magnitude of energy can a fault release. Are there directional issues there? Where are they relative to the bridge site? What's their historic activity? I need to understand the path through which those seismic waves travel. I need to understand site characteristics. Is it a clay site? Is it a rock site? Is it a sand site? Is there water present or is there not? All of those change the site motions, how the seismic motions, they propagate out from the sources, they get to the site, and then how those seismic motions propagate up from deep into the surface soil where the bridge is touching the ground and interacts. You need to understand how that superstructure and how that foundation interact. We call it soil foundation structure interaction. The soil affects the bridge affects the soil as it reflects back. Then we need to understand about the structure, and then this is what's exciting, transportation capacities. Across the state of California, across the country, the standard for earthquake engineering for bridges is no collapse. Seismic safety, we associate no collapse with no loss of life. Okay, that's the standard. Okay, and that's what the codes are based on. Well, the Governor's Board of Inquiry and the governor directed us for these important bridges like the Bay Bridge. All of a sudden, now there's this new standard. The community is communicating to us and trusting us with funds to go out and select a bridge, design a bridge, build a bridge, and maintain a bridge that's going to be operational or to offer service, emergency service to the community, Oakland, San Francisco, et cetera, after a major Bay Area earthquake. That's unprecedented when we started this. That means my team could not go to a bridge code, open it up and go, okay, here's the load cases, or these are the things we have to consider. This is how much load this member can take, this concrete can take, this steel can take. Okay, so we were asked to do something a little extra. Now that's not to say we're not going to have some cracked concrete, we're not going to have some bent, spalled concrete, we're not going to have some bent steel, some deck joints aren't going to be damaged. That's going to be true. But the idea is, can we get a lowboy tractor trailer rig? Can we get a fire truck? Can we get a D7 on a lowboy truck? Can we get emergency equipment? And can we open up the bridge to public quickly? Okay, that's a new challenge. And because I don't have codes, we had to literally develop it from almost first principles. And when engineers have to make judgments, we don't like to do it by ourselves. Engineers always like checkers. We like criticism. That's usually a good thing. We like to talk among ourselves. And we welcomed having an external independent review panel on the Bay Bridge. A lot of people don't like that, but I love to have people looking over my shoulders. Well, Joe was one of the people. He was the chair of that group that looked over our shoulders on those judgments. Okay, very, very important. I could spend 2 hours talking about that. Next slide. So the challenge was unusual, and I think quite frankly, right now, I'm feeling we're really having a lot of success right now, and I really give Joe a lot of credit for that. Next slide is geology, and Joe was very aware of geology. Remember I told you he was on SEOC, Structural Engineers Association, Northern California's seismology committee. So he had to deal with seismic motions, and when you deal with motions and how they change as they propagate through sands and rocks, you have to think about geology. You have to respect it, you have to understand it to some degree. Next slide. Joe was extremely supportive of that. Now, just to give you a sense of why is geology so important? Why are the foundations important? I find the foundations more interesting on the Bay Bridge than the rest of it, just because in some cases, there's more foundation under the Bay Bridge than there is superstructure. Like, for example, the Skyway. At the waterline, the Skyway goes down 300 feet. It goes up like, like 150 feet. Okay? So there's actually more structure going down, and that's because the geotechnical conditions are poor there, and actually that caused a lot of problems in the Bay. The Bay Area Bay Area is a poster child for poor soil conditions, and we have to pay attention to that. Joe is very supportive of that. Here's a picture of a building from the 1964 Japan earthquake. Okay? Obviously, something went wrong here. The people that came out of this building, the windows opened up, and people walked down the side of the building. I know that because I have participated in US-Japan earthquake and wind workshops as we exchange technologies. And I was told that by people that were there. Okay? Imagine that. The structure, the building part was so strong and stiff. Okay? Both two different things. And strong is always good. Stiff is not always good. It may or it may not be. And here it didn't really get tested with respect to ductility. But even if the building has been designed very well, obviously, and the foundation is not, you can't have a structures engineer going, I got the structures part, and then ship off the geotechnical part. And that's usually what's actually done. They're usually two different fields of expertise. Okay? Joe was very supportive about keeping geotechnical engineers together with the structural people. And that's unusual, and I had problems keeping people together. And actually, my geotechnical engineer is sitting right here, and you know, he goes everywhere with me. I don't make decisions without him. So Joe was very supportive of that, and that's not always easy to do. Next slide. So it's important. Those foundations are important, particularly on the bay. This is a cross-section. If you could magically cut a section from Yerba Buena Island to over Oakland, there's the existing bridge. This is what you would see. The rock is like this, goes down as much as 450 feet below the mole. Various layers, complex layers of sands, muds, old bay muds, new bay muds, etc. Strange lenses here, and it's not all the same. As you move out to you or you move in, these formations change shape. So it's a three-dimensional problem. Next slide. That's just the soil. Okay, because of that, okay, we did some new, we were challenged to do something different. We were challenged to, this is going to be really hard. So what we did is, again, with the support of the external independent peer review panel, we mobilized an offshore exploration platform. Okay, this is not normal. But if you think about the Bay Bridge foundations, they pretty much are offshore oil platforms. Okay? Now, one of the problems that normally we have in building anything, a big building or a bridge, sometimes when you go out and you take a soil sample, could be a sand, it could be a clay, it could be rock, and then you pull that soil up, you pull that soil sample up, you classify it, you properly contain it, and then you transport it to a laboratory, and then you test it. Well, the reality is sometimes as you're bringing it up, packaging it, transporting it, it gets vibrated, it gets moved, it gets disturbed. The quality of the data that you're going to get from the test is contaminated. Okay? We call that a disturbed sample. There's still value to it, but it's not as valuable as what you'd really like. Okay? And sometimes they just plain flat out get lost. Okay? That's the one that really gets us mad. Well, what we did is, new challenge. Okay? With the support of the peer review panel saying, yes, this is a good idea, we support it. The people that we work for offered to allow us to go out and rent a laboratory and stick it out, stick it out on the drilling rig. Okay? So the transport of the soil samples were from this rig to that trailer. Guess how many samples we lost from here to here? 0, not one. And how much disturbing of the soil samples do you get from here to here? It's great. Okay? So we were getting information instead of, you know, in a day or instead of weeks or maybe even months. We were literally at the end of one day getting first draft results of what the soil properties are. Okay? Next slide. And if I can take you inside that lab, it was not luxurious, but we had triaxial soil testing machines. We had rock testing machines for when we got really deep or when we were near the tower. We also had devices to essentially bake the soils to get the dry unit weights, et cetera. I mean, we had a full functioning laboratory. Next slide. Because we were out in the bay, we also wanted to do some tests down deep. We didn't even want to bring them up. So here's an in situ probe. In situ means you're doing a test. You go down 300 feet and do the test there. You go down 100 feet and you do the test right there. And you have pressure control here to deform this probe in a variety of different ways. And then you also have measuring devices within this probe and along the side of the probe and in the tip of the probe. And that information is combined with the pressure to give you soil properties. Okay? Next slide. That allows us to have a tremendous amount of information. We had more information on this bridge than, quite frankly, geotechnical, I think, any bridge we've had, because I think we had to. Next slide. And what we can do with that is basically create three-dimensional maps. So you're looking at a map. This is like from above. And remember when I told you if you cut from here on Yerba Buena Island all the way over to Oakland, you would see variations of sands and clays and rocks in various locations. But I said it would be different if you moved out into the audience or you moved away from the audience. So if you move south or if you move north. These give you, these blue lines, light blue zones, yellow lines, map out different types of sands and clays, et cetera. Okay, so this is a 3D geotechnical map. Okay, without that kind of extraordinary geotechnical exploration, we wouldn't have been able to know this kind of thing. And that affects how we think the seismic motions are going to be impacting the foundations. Next slide. We could also create, from that three-dimensional information, some images that people could recognize right away. So there were fewer miscommunications. That leads to better everything. Next slide. That also led us to consideration of, with that extra information, having a different type of foundation. Battered piles, and I have the models out there so you can actually feel the difference. The exact same pile cap, the exact same bottom fixity, the exact same piles, those 4 dowels, I use that in class to allow people to actually take measurements of, you can push it over an inch, and how much force does it take to push over that system 1 inch. Okay, you'll get a different number for the battered piles. Well, with the large seismic motions out in the bay, and we're talking about over a meter of movement in some locations in a seismic event, depending on the frequency of the structure and how tall it is, et cetera, okay, in some cases. How do you think about how do you make sure this bridge is going to be operational? Now think about the Bay Bridge, and the bottom of the Bay Bridge is not the pile cap, it's not waterline. The bottom of the Bay Bridge goes down a lot deeper. Those piles reach down. The reason you have piles is because you have to reach down through the material, reach down through the water, then reach down through the material is not competent. If we had rock, we could have a spread footing. That'd be really cheap. But you use piles to reach down deep, deep, deep until you get to that competent material. So sometimes you have to go 50, sometimes you have to go 250 feet down to get to that competent material where you really get approximate fixity in the foundation. So the Bay Bridge is a lot taller, effectively, in a seismic event than it appears visually. It's a lot taller. That means it's a lot more flexible. We anticipate, I believe we are going to see someday, potentially, movements of as much as a meter. Well, if you think about movement in an earthquake of a bridge at the roadway level, moving over a meter, it's not going to come back, not completely. Part of it is recoverable, part of it's permanent. Okay? Things only come back to zero in elastic computer programs and on a blackboard at a university. Out in the real world, they move, and part of it is recoverable and part of it's not. And that became part of the design. So we have to manage that displacement. And that was a real challenge on the retrofit. Well, here, these battered piles, like in the models that I have out there, if one of my friends here was to push me at my shoulder level, I'd be very flexible with my feet together. If I move my feet apart and they push me again, I'd be a lot more rigid. Okay? Sometimes it's good to be rigid in earthquakes, sometimes it's not, depending on what you're trying to do. It is a design variable. Okay? This was very good for us because it did 3 things. First of all, it kept the displacements at the pile cap manageable. Okay? And the permanent movement up here, or the movement up at the roadway level, is a function of how much this moves over, plus its rotation. Because this is a function of how much the pile cap moves over and how rotated the pile cap is. Because the displacement up here is the translation at the pile cap plus the rotation at the pile cap times the height up. So you get a double whammy when this moves. So to keep this in alignment, and I've been on lots of bridges after earthquake. Northridge, we saw lots of bridges that were permanently moved over 1.5 inches, okay, 2 inches. Grind the deck a little bit, the bridge is open. In fact, nobody even slowed down, okay? So bridges do move a little bit in earthquake. Now, a little bit of movement, it's not that big of a deal, but again, afterwards, I can't have something moving out a meter and then coming back and it's 1.5 feet off. That's not going to work. Things aren't going to line up, especially on the old bridge where we have already narrow lanes and no shoulders. Okay? So that's the first benefit. You can manage displacement here and manage displacement here very, very well. Okay? Then the second benefit is the pile cap gets a lot smaller. And the reason the pile cap gets smaller is because you have to keep the distance between the piles a certain distance. Have you ever nailed 2 2x4s before together, and you put in 1 nail, and that holds them together a little bit? Put in 2 nails, and that holds them together a little bit better. Now you put 6 nails in. Well, what happens is you start tearing up the wood. All of a sudden, it doesn't work anymore. Same thing happens with piles. You have to have them spread out. The crummier the soil is, the more you have to have them spread out. Well, in the Bay Area, you've got to have them spread out a lot. As the pile caps get spread out, this pile cap starts to get really, really big. Now all of a sudden you have more mass, you have more weight. In earthquakes, F equals ma. It doesn't always work that simply, but that's usually the wrong direction. right? So this allowed us to have less mass, which actually led to less displacement, less earthquake force. So it actually was another good thing. The third good thing is as the seismic waves propagate from the Hayward Fault, they come over here down deep in the rock, and they propagate up. Okay? Where these energies, as the soil passes the wave up, it tends to grow, it tends to get worse, it tends to get larger. And it's frequency dependent, it's complicated, but it tends to get worse. Well, these battered piles, the point of fixity is deeper. Okay? And what that means is most of the energy, where this pile is truly connected or effectively connected to the earth, it's down lower. So the actual motion that's coming in from the seismic propagation of waves, the motions that actually get up into the structure are actually smaller. So you get 3 successes for 1 challenge. Okay? Now there's no free lunch. Okay? Battered piles are harder to put in. You know, it's like if you nail down a nail on a piece of wood, putting it in straight's really easy. Okay? Now do a couple of studs, and now you have to toenail it in, right? That's a lot harder, right? Well, same kind of thing happens here. Plus, these battered piles, these types of piles, even though the pile cap would be larger, these are normally or very commonly just designed as penned. The top is penned. All you have to do is transfer one kind of load, shear, through there. As soon as you have something like this, now you have not just shear, you get a double whammy. Now you have to design for not only 3 shears, but now you have to design for 3 moments. And moments are basically a twisting kind of behavior, a twisting kind of load. Okay? So there's no free lunch, but if we were to have the piles like this, the vertical ones, we would actually end up having a lot more piles, and we have a lot bigger pile cap. Okay? And I've seen jobs go that way. Next slide.
Excuse me.
Yes?
Can you go back to the previous one?
We've been asked to go back one. Yep.
What are the benefits of having that space between the silt and the pile caps with the open water going in between the piles?
Oh, you mean over here?
Yeah.
Little or no benefit. At the very top, the interaction that takes place between the water and the pile cap, the example that I use when I teach structural dynamics is imagine you're in a bathtub and you put your hand right at the surface and you move your hand back and forth across the surface. You know how you create like a little tsunami, and as you push your hand forward on this side, on the forward side, you get a heaving of water, and on the backward side, you get like a sucking down of the water, right? Well, what you're doing is you're doing work. So you get energy sucked out of the bridge system from the top water. But down low, it's different. Down low, you put your hand deep in water and you do this. The surface hardly feels it, and it's really hard, right? So it's a very complex interaction that takes through this water, and some of that water that's right around the pile cap, actually gets excited too. That is, if you accelerate the pile cap this very quickly, you actually have to accelerate the water there, right? And it becomes a very complicated mathematical problem. But that is usually a 5 to 10% effect. But we do account for it. But there really is no benefit.
You're talking about in an earthquake?
Yes.
The energy, okay.
That's right. Because the structure starts moving around, and it has to move through that water, just like your hand has to move through the water. And it's interesting. Earthquakes, usually people think about them as accelerations, sometimes displacements. But this is a velocity, another kinematic variable. Interesting topic. If you want, I'll be happy to talk about it afterwards, as much as you want. Next slide. Okay, and from that, and again, Joe Nicoletti and the peer review panel, without their support, we would not have been doing this and saved this money, and I actually think made a better structure. We didn't have a lot of experience doing this. The offshore industry has been doing it for 2 decades, so I was very confident it could happen, and so was Joe. Okay? However, we need to teach our contractors, the people who work on Caltrans jobs, to be confident that they could, if you will, toenail in those piles. And we had specifications, because if you're fabricating a pile cap someplace and the piles don't come in exactly at the right angle and you're trying to weld them up, the fit up is bad, you got a problem. So what we did is we were, with the support of the peer review panel, we requested to do a pile installation demonstration project where we actually practiced putting these in and welding them. Next slide. Okay, where we actually went out, put these in, 2 of them, at an angle, 1 vertically. Next slide. Okay, here you can see the angle. Not a big batter. Next one. Okay? And with the hammer, this is a hydraulic hammer. This is the kind of this is the hammer that actually drives down piles. One type of hammer. Next slide. Okay, now you're going to have to push the button several times. Okay. Now there's effect when you, yeah, here you go. That happened pretty quick. Let's go back and do it one more time. Go back one more slide. Okay, now push enter one more time. Okay. When you drive, you impact a pile with a pile hammer, you send a shock wave out. Okay? And that shock wave is a threat to marine life. Okay? Next slide. This is what that shock wave looks like. Okay? Next slide. And with that demonstration project, with the support of the peer review panel and the people that we work for, we were actually able to try out barrier developments for ways to deaden that shock wave that threatens marine life. Next slide. And one of the things that was developed and implemented, and we're still using it today, I don't really think that we're the leaders on it, but we're certainly at the table. We create a marine pile driving energy attenuator. Some people call this a bubble curtain, but I think anything that costs a couple $1 million, I don't want to call it a bubble curtain. I like to call it a marine pile driving energy attenuator because that's really what it does. I'm sorry, I'm really a nerd, aren't I? Next slide. And again, and now we have to do this. Now it's required and in many states. So it's important that we had a chance to practice it once, and it really made things better in our construction site. Also, with those waves, Joe Nicoletti, I told you he was on the SEOC seismology committee. He also really helped us in developing seismic waves too. Okay, and I could talk for 2 hours about that, but I'm not even going to start because if I do, I won't be able to stop. Next slide. Okay, and that made this possible. So here's a challenge, and we actually had like 4 benefits, and they were actually spin-offs. Interesting. A return on investment. Next slide. That I think we're going to continue. Well, how does all this work? How does this all respond in an earthquake? Next slide. Well, first thing, what we did in the design, we didn't just let computers start telling us what to do. Don't let the numbers drive you. Your numbers are your checkers. Your numbers are your guides. They're checks on what you think. Right off the bat, the structure was designed. How's this going to work? And this is an elevation image. It was actually the ones that we presented to EDAP, the Engineering Design Advisory Panel, where we actually showed these red dots are where we said, this is where we're going to take damage in an earthquake. And we're going to invest a lot of attention and a lot of care in the design and the construction of these. So we're going to focus it. Now, why should we focus on that? Why should we pick where we're going to have some damage? Well, think about the fuse in your apartment or your house, right? Do you, if your house gets struck by lightning, do you want to tear out the walls and wonder, is there a wire someplace that's ready to burn down your house or apartment? Or do you want to go, I know where I chose in my electrical systems on every single circuit where the area is that I chose to be the fuse. It's the fuse box, okay? These are structural fuse boxes, and we picked them right off the bat with Joe's support. Next slide. Did the same thing in the self-anchored suspension bridge, particularly in this bridge, because it's so unusual. There's lots of experience on a Skyway type structure, lots of experience on an Oakland touchdown kind of structure. Not a lot of experience on this kind of structure. So we wanted to be very careful. And this is not about how fast your computer is or how cool it is. This is about plain old thinking. And you know what? Joe Nicoletti is a very sophisticated guy, but he's also a really good plain old thinker. A wise man, I would say. Next slide. Okay, however, we still use our calculations. We still do the very best we can at predicting how the structure is going to respond during all kinds of different events. This structure has been modeled, analyzed, up, down, sideways, backwards, and forwards. And I'm just going to bang through real quickly to give you a sense of kind of the things that we presented to Joe Nicoletti and the external independent peer review panel. We did this all the time through design. This is a shot of the Skyway of our model. Next slide. This is a close-up of just one of the columns, superstructure, and every single pile is modeled, and these elements are models that are the soil structure interaction. So these models, these elements, have characteristics, strengths, stiffnesses, damping properties, et cetera, of the soil. These have strengths, stiffnesses, material properties, yielding capacities of the structural systems. Next slide. This is a close-up. This is our pile cap, same piles. Next one. These are finite element models. This is a finite element mesh that we used on the pile cap. Every single one of these cubes represent a small finite element that is combined with all the other finite elements together. Every single one of them has, X number of degrees of freedom depending on the type of element you choose, and then all of them have to be solved together. Some of these represent tens of thousands of degrees of freedom. What that means is there might be tens of thousands of equations that have to be solved simultaneously. These are some of the most advanced software tools in the world. Now, I don't like state-of-the-art because state-of-the-art art in an engineering environment is unreliable. There's blood on the cutting edge. So I'll leave that to somebody who doesn't need to be productive on a date. When I say I'm going to finish something on a date, I have to do that, or there's going to be something to pay for that. Okay. So what we do is I like to go back one step. What's reliable? What's been proven reliable? What's professionally supported? So we used ADINA. I like to use ADINA. I think R&D, ADINA R&D is very good company. We also like to use Ed Wilson's SAP. So I like to have two different pieces of software checking everything. So we check the people, and then we check our calculations, and we even check, if we're going to use computer models, we check the computer models. Next slide. This is just a finer look into those pile caps. That's the annulus where the piles go down. Next slide. And then we go right into the piles where they connect and they come up into that annulus. So there's been a lot of finite element modeling of this system. Next slide. Because it's right next to that fuse. I need to make sure the material right next to that fuse is going to work well. And these computer models and our calculations, we actually have to go out and build them. Next slide. And it looks pretty much the same. Okay. Now, the next couple of slides I'm going to show you real fast, I want you to know they've been magnified. Okay. So these are snapshots of how we believe the structure is going to vibrate or move around in an earthquake. Okay, and they are magnified. The reason we magnify them is because when you print them out on paper, you look at a computer screen, you want to see things. It's like if you want to read the really fine print on a contract you're suspicious about, you want to pull out the magnifying glass and you want to read those. You want to inspect it. Okay, so engineers do that all the time. We like to use magnification. Next slide. Okay, and just like I like to tell students that sometimes you're in a different mood, right? And you might behave differently with the same input, okay? Or you have lots of different feelings and they all combine together to produce your attitude that day. Structures have something kind of similar, okay? They have different modes. They have different types of behaviors that are a product of their material properties, their geometry, a whole host of things. And some of these images I'm sharing with you are what we showed Joe Nicoletti. And we have a sense of what these behaviors or what these modes should be. Okay, so they give us a check, and again, we amplify them, we magnify them to just make sure we don't miss something. Okay, next slide. Okay, now this is a model of the bridge where we need to model the different types of bridges all together. Okay, this Skyway bridge affects the SAS. The SAS affects the Skyway bridge. So there's interaction. So you can't do just the Skyway and then do the SAS. Like it or not, at some point you got to do them all together. Okay, so this gives you a picture of the kind of thing we would show Joe Nicoletti in the peer review panel. Next slide. Okay, and again, they're amplified, they're magnified, okay, just so to make sure that we see it. The bridge is never, we're not predicting this, okay, but it's magnified just so we get a sense and we get a sense, okay, up, down, and are the vertical behaviors combined with the transverse behaviors. Sometimes the behaviors are not independent. Sometimes they're coupled. Sometimes they act together for various coupling reasons. Next slide. Next slide. Next slide. Next slide. Again, we amplify them. Transverse. Next slide. Next slide. Okay, now these are things that we showed the external peer review panel. These are maps of strains and stresses that we predict we may see in a large event up in the shear links. This is one of those areas where we spent a lot of time making sure we understood it, we designed it well. We even understood the elements next to these, the parts of the tower next to them, because we didn't want these damaged. We wanted these much stronger than these, and we wanted these to be tough, that they can get bent like a paper clip, right? You don't want to buy a paper clip that you can only use once. You want a paper clip that can be bent back and forth a lot, right? It can be used a lot of times. Well, we want shear links that can be bent back and forth a lot of times. Okay? We want a tough thing. But over here, I want the pieces that connect into that. I want to make sure that's stronger because I don't want any damage in that tower. I can't fix the tower, but I can fix these. We can bolt these off. Okay? These are the kinds of things that we showed the external peer review panel. Next slide. A lot of modeling. And we even have information that we developed and shared with the peer review panel that describe how, as the shear link deforms up and down from one edge to the other through relative displacements, what that load is, and these are hysteretic loops. This basically is a characterization of how much energy is going to be absorbed and how much permanent deformation we're going to have in that member. Next slide. Okay. We don't just trust that. Not only we're in that place, now I tend to like to go in the lab. I'm a lab rat. I like to test it. Now I've got my best calculations. Let's go make sure they work, especially if we haven't done one of these before. Let's not be the first to do something unless we've actually done it before. Well, if you can't go out and build one, why don't we build one in the lab and test it? So here's a shot where we did some inelastic column testing down at UC San Diego on the Skyway. Next slide. And we actually pushed it back and forth against a strong wall to almost double what we expect if we have a 1,500-year event. And we made sure the damage here was acceptable, to acceptable levels, and it was exactly where we wanted. And we wanted to make sure that pile cap was still absolutely stronger than the yielding area, and we wanted to make sure this area was fine. So we went down and tested it. Mr. Nicoletti and that peer review panel, they were there. Next slide. And then we do back checks, back calculations. These are characterizations of how much energy these things can take. And these are very, very tough. This is the load it takes to push over a column. This is how far the column goes over. Next slide. Did the same thing with the shear links. Those were at UCSD and up at University of Nevada, Reno. We go to those places because they have very, very unusual laboratories that can do some amazing things. And they get stuff done on time. Next slide. Okay. Also at Nevada, Reno, we actually built elements of the tower on either side, and we put a shear link in here, and then we cycled it back and forth to levels that are actually larger than the 1,500-year motions we're designing for. Next slide. Joe Nicoletti was there. Then the same thing, we back check into our original calculations. This shows us that we have, if this is the seismic 1,500-year demand that we're designing for, this almost straight line shows us there's hardly any damage at all, even at that level. There is some, but not much. But if the earthquake is even bigger, it can continue to hold its load. It can continue to hold load and just deform more. But that's if we have a larger one. We also did a check of, let's just take out the shear links. Will we still meet it? We would. So we could actually lose all the shear links, which we never will, because we're putting so much energy into making sure they work. Next slide. These are things, again, we gave to the peer review panel. And this is a final check on push the whole tower over. And from all of that testing, not only do we have our calculations, we actually did things in the laboratory, and we can check our calculations. Next slide. So we develop experience. Joe also helped us not only get support to do certain types of testing and learning, but remember that last challenge about transportation operations after event. Well, deck joints are things that nobody ever really worked on till mid-90s. Because, again, the standard is no collapse. Well, deck joints, who cares? You throw a steel plate over it, and you throw some asphalt on it, and off you go. If that's the only problem. Well, here, if we're going to be operational, we don't have 20 years of research on deck joints, but we can develop something fast, and we can do the best job we can. So even though our design calculations show the deck joints are going to be fine, we still wanted to build some, go into the laboratory, and verify that even though we don't have 20 years of experience or testing or 20 years of experience on bridges actually in the field, we could go in the laboratory and try out some of these and drive them with our seismic motions that Joe helped us develop, the rest with the peer review panel and Dr. Idris, to drive this like a piston very, very fast and open and close this and move it around to verify or check how's this going to do in a large earthquake. Next slide. We also even developed a new single plate deck joint being used right now on the South-South Detour on a smaller scale, but we're using these on either side of the SAS because of its large, about 1 meter potential movement. Okay, we actually build one in practice building it. Next slide. And this is right at Pier 7 at our construction site. We brought down the UC Davis roadway paving testing machine. This is something you drive down and there's a wheel that goes back and forth, back and forth, back and forth, and you test paving. So what we did is we placed this thing over the top of that deck because there's a famous bridge, I won't mention it, that they replaced their deck joints, and the first day a truck went over it and it failed. Okay, not going to happen here. So what we did is we built it, and then we put this truck wheel load on it and went back and forth for about a month. Okay, no signs of damage. We started getting tired of watching it. So what we did is we upped it to an airplane load. So what I can tell you from this research, we can handle about 10,000 landings of a 737 before we're going to have problems on this deck joint. So I feel kind of good about it, at least from the early research. Next slide. And it's appropriate to not take risks on Interstate 80. Okay, then we have to go out in the field. And again, I want to tell you, Joe Nicoletti and the rest of the peer review panel were there. He made contributions out in the field. This is a shot of the Skyway. Going up, next slide. Another shot of the Skyway. Intense. He was all these places. Next slide. This is a shot of Stockton. Stockton was part of our construction site. This is where we fabricated a lot of the Skyway structures. More than 450 of these. Some of them 6, 7, almost 800 tons. Very, very heavy. Next slide. Another shot of it. Next slide. This is Joe Nicoletti out in Stockton with Bruce Bolt and another inspector. This is one of those segments, so it gives you a sense of the scale. So this is a guy who basically, community service, and he's doing all this stuff. I mean, he could retire, and he's retired president of a very fantastic structural building firm, and he's still giving to the community. Next slide. And then, of course, a leader doesn't try to do everything himself. A leader tries to use the people that are around him because that makes the team better. And this is Dr. Sibley, who's also on the peer review panel. Here he's looking at the West Loop saddle, the self-anchored suspension bridge. Next slide. And here this is Dr. John Fisher of Lehigh University, also the creator of the Atlas Labs, bridge expert around the world on steel bridges. And I think I see a star back there, the director of American Bridge Floor Joint Venture, who I think is here in the audience. Star-filled picture there. Next slide. Okay, one of the questions, or one of the things I wanted to make sure we covered, where are we? What's the status? So I'm going to put you in a little airplane real fast, and I'm going to simulate a real fast flight. So what we're going to do is we're going to take off from Oakland Airport here, and we're going to fly a loop around the east end of the Eastbound Bridge. Next slide. Okay, so here we are in the airplane. We came up from the Oakland Airport, and now we're swinging in to Yerba Buena Island. Okay, so this is where we're approaching the Bay Bridge. Next slide. We're flying in a little faster, and now you start to see the westbound structure of Oakland Touchdown the structure is complete, and we're missing a little spot right there. Next slide. Now we're getting a little closer. You see that gap? Now this is something that Joe Nicoletti really supported. I want you to note how the lower deck comes out on the Bay Bridge and it swings wide now. This is where it used to be. This is where it used to be. This is called the Oakland Touchdown South-South Detour. So with the peer review panel's support, we did something bold. Okay? We were going to be working on this, and it might have been the critical path to opening up the bridge. But with the support of the peer review panel, the team struck out on something bold to have a widening of the eastbound roadway out about 12 feet, about one lane. Right? Then, once the old eastbound was opened up, we could actually widen this portion by a lane on this side of westbound. Then once it's widened by an extra lane, then we can cut the lane off on this side. Once we cut the lane off on this side of eastbound, then we can finish this one. This is called the Oakland Touchdown South-South Detour. I think it saved us 9 months, okay, without the peer review panel saying this is a good thing, you should do it, and advising the TBPOC, I'm not sure it would have been done. Very bold, the return's been unbelievable. I'm very confident we got at least 6 months out of it. Next slide. Okay, we're flying over it. Now you can see there's construction going on right now. Next slide. We were not going to be able to do that until we opened up one of the lanes. So way ahead. Okay, now we're looking backwards out of the back of the airplane. Next slide. Okay, next slide. Go ahead. Okay, now we're flying out toward across the Skyway. You see the old structure there. Now you're starting to see what's going on in the SAS. The Skyway is complete, has been for a while. Next slide. Now as we fly over the SAS, you see all the boxes there. You start to see the cables coming up. Next slide. Okay, see the tower there, the cables. Next slide. Box is incomplete. Tower's fantastic. Box is fantastic. Cables coming down. Now you see Oakland Touchdown and their work going on in the connection. Next slide. Now we're flying a little too close comfort to either of our contractors, but you know, we're daring. And what you see is the westbound structure of YBI is essentially complete. And they're working on eastbound. Actually, this concrete has recently been placed. American Bridge Floor is doing an amazing job on this piece. This is a very tough, closure pour is not the right term for it. This is a very difficult connection. This is, these two types of structures are very different. And they need to work well together always, under all conditions. So this is almost a mechanical type of system, and we've got quite a team working on that. So this is underway. Actually, two very significant concrete placements have been completed, and they're not too far away from starting to move on this. It won't be long until the deck will go on. Next slide. Now let's say the airplane was a seaplane and we land over in Clipper Cove, and you look back. I wish the lights allowed us to, but what's exciting here is you can see that the suspenders are up. And actually, American Bridge had well, they're actually up to about 80, well, over 80% load transfer onto the suspenders, and now they're working on distributing that load evenly among all the suspenders. Next slide. Okay, and again, Joe Nicoletti was there, has been out there with us. Actually, Mr. Peterson has actually allowed us to move out around a construction site, the SAS, with the peer review panel very openly, which really helps. Now I'd like to ask Bart Ney to come up, and he's going to walk you through one of the most exciting things on the job right now.
But one of the things that I want to say before we go into this is how much third-party external review has meant to this job. And so every time he says that name and he talks about the Seismic Peer Review Board, that group is external to Caltrans and the team that's actually building this bridge. So third-party review has been a big part of what you've just seen of every element of this project. But they are not the only third-party review that this project has gone through as we've moved forward. With the TVPOC, the Toll Bridge Program Oversight Committee, Caltrans, the Bay Area Toll Authority, and the California Transportation Commission are working together to build the bridge. And the Bay Area Toll Authority has its own inspectors and engineers working hand in glove, day to day, with the project team to make sure that as we move forward, another set of eyes has followed us all the way through design, well, most of the design before this, and then through construction. So we have that element. And then we also have the Federal Highway Administration, who's been involved throughout this. We regularly brief them. They came out, they were out yesterday, to follow us through the process. So third-party review is a big part of the construction of the Bay Bridge. And the other thing I wanted to say about tonight is it's sort of the marriage of communication and engineering. And Brian has been talking about some of the things when you look at the bridge with just your naked eye. It seems simple. And now you're seeing, just how complex some of those simple things are. So why bring up the public information officer to speak about one of the most complex things that you can see, besides that Brian needs to rest his voice and get a drink of water? The reason for that is how important communication has been on this project. We took months to actually create an animation that would give people an idea of what it is we're doing here, because it is complex, it hasn't been done before, and it's very important that we get this right. Engineering has to be right, the contractor has to be spot on, the teams that are working out there, the skilled labor, have to beat the learning curve and do great work. And we're very happy to say that this is proceeding quite well right now. There are 3 phases that we're about to go through with load transfer to tell you a little bit about what that is, and we'll bring you up to speed on where we are right now. So that's the reason why we have these assets. We wanted to make sure that the public understood exactly what it is that's happening at this moment. Lifting 35,200 tons of steel isn't done every day on this job, and you've heard some big numbers thrown out here. Brian talked about 452 individual segments in that Skyway, some of them weighing 600-700 tons, all being lifted up to heights of 150 feet. This is 35,200 tons at once. So the animation that we're about to run, most of the processes that you're seeing are happening simultaneous. We have to show it in a linear fashion. But imagine that all these things that we're about to talk about are happening at the same time. So go ahead and run the animation, please. I'm not going to be able to pause, so I'll try and go auctioneer with you and talk about what it is we're seeing here. Okay, so that's situated it's the self-anchored suspension bridge naturally. And when it's first built, it's supported on a temporary frame and the tower's up there. And we have to pull the tower back about 18 inches towards the Yerba Buena Island because the weight that's about to be placed on the long span would pull it the wrong way. So it's pulled back, the cables are put in place. This is the process that we use to pull the individual cables. The strands, there were 137 strands, 127 wires in each strand. And this is the system we used to put that cable system in place. And then after the cable was put in place, we're going back in time here a little bit to show you some of the steps that happened before load transfer. The cable had to be compressed. You had that hexagonal shape, and then you compress it so that it gets the cylindrical shape. You start at the top of the tower, work your way back down so that you can get rid of the voids that are in the middle for the most part. And then anchor it down. This is a self-anchored suspension bridge, so the cables are in splay chambers that are inside the roadbed themselves. Okay, and then we have to place the cable bands, and each one of these is actually unique. There are a bunch of different types that are placed. There are 114 different ones that we put out there. They were all placed on the cable so that we could hang the 200 suspender ropes that would ultimately hold the weight of the bridge. So this is one of the typical ways that we used it. And this, again, it's animation. A lot of credit goes to the trades. There are humans out here that actually have to make this all work. These are the mechanisms that we've used to lift these things up into place 200 times. And then here you can see the cable saddle a little bit better. You can see the groove that the suspender cable has to go into so it can come down and connect down into the bridge deck. One of the unique things about this bridge, because we have one main cable going across, is that the suspender ropes are going to come down at an angle and anchor off to the side instead of straight down like you normally see on a suspension bridge. So now we're getting closer to load transfer. We're making the connections of the first set of cables that are going to take the weight. So the steps of load transfer, well, it starts off that the bridge is being supported by this temporary falsework. And then we connect the first 104 cable strands, and they do the heavy lifting. You can see how much this cable is moving in phase 1. This is phase 2, the ropes closest to the tower, and phase 3 is the distribution throughout for the rest of the cables. So almost all of the load is being picked up in phase 1. Now, these are the individual steps that are happening simultaneous to do load transfer. And one of the reasons why it's so challenging. There are 8 crews out there right now doing this. Look at how much that cable's moving. It's moving 30 feet in one direction, about 15 feet in another direction. A lot of articulation going there, and a little bit of lift. So we go a little closer into the detail of what's happening here. You can see the jacking mechanism that's actually pulling these strands down, going to connect down here. And when you're doing big things, like Brian says, it's good to keep them simple. So you'll see how these pieces are coming down and connecting and basically bolting in. Now again, with all this is happening simultaneously, we're just taking another look. We're going back in time and taking a look at the liftoff here. A couple feet in some areas of the bridge, it's less than others. Then after we get through load transfer, this can be lowered and taken out because the weight is now on the cable system. Now, while load transfer is happening, the bridge is moving. So certain parts of the bridge we don't lock down so that it has to come into its final geometry, its final placement. So you can see the deck moving there. Those parts of the bridge weren't locked down either. We'll show you that in a second. The back end of the bridge is our jacking saddle. You can see there's a giant cavity back here, and it's designed so that we can press on this part of the bridge, get the tension correct on the cable system. Steel plates are placed until we get it to the right length, the right position. And then once we've got that, the jacks come out, we place rebar in here, we grout or concrete the open space. And it doesn't move again. During this process, again, we've gone back in time. This is all happening simultaneous. We start releasing the tower, and that 18 inches comes back to plumb. That's how we ensure that the tower stays straight up and down. And you can see some of the hardware starts to get placed. Here, that's for the cable, shrouds. And now, once load transfer is complete, we can start doing the other things that are important to protecting this bridge. The next steps that we're going to be doing after load transfer is wrapping the main cable. So we've sort of have an S-wire wrap here that goes around the outside of the bridge to protect it from corrosion. There's a paste that's used on here before we actually do the wrap. The wire wrap goes around the outside, bay to bay between these cable bands, and then paint on the outside of that. Now, the bridge isn't going to be in perfect alignment after load transfer and some of those other operations. And this animation shows this a little too perfectly as well, but we've done that to give you an idea of the types of things that have to happen. This is the area between the Skyway and the self-anchored suspension bridge where we'll be using jacks to get this alignment to a point where we can actually put the joints in the way that they're designed. And here's a look inside the bridge at the hinge pipe beam, one of those fusible elements right here that Brian was talking about. They're stored right now in the Skyway. They'll be slid across to connect into the self-anchored suspension bridge. Connected so they won't move on one side. They're stainless steel on the other side so that it can slide in an earthquake and day-to-day with expansion and contraction. Then once we've got that where it needs to be, then the plates can go over the top of the joint. And other hardware elements can be placed because the bridge is finally settling into the geometry, the place that it needs to be. And if we're smart, we didn't lock down these things. These are bearings and shear keys. They allow the bridge to move in one direction. They control the motion a little bit in the other direction. Now that the bridge has stopped moving in large quantities, we can pin them down. Put these rods through, bolt them down, grout them. There you go. Grout them. And remove some of the temporary supports that have had to be there in the meantime to hold the bridge. Now it's starting to look like the suspension bridge it's meant to be. We can begin taking down the scaffolding and get ready for opening, at least for the self-anchored suspension portion of the bridge. So as I get ready to pass this back to Dr. Maroney and others, I'd just like to remind you that there are some exhibits out in the lobby that show some of the steel portions that Brian's about to talk about. We're about to show some other quality control methods, and at this point I'd like to ask Dr. Maroney to come back.